Today we're talking about comparing two quantitative variables. In other words, scatterplots. Well, actually we'll be doing some other things other than just scatterplots, but for now, scatterplots. Okay, so up until now we've been talking about individual variables by themselves. Maybe we want some histograms of people's heights, or a box plot for shoe sizes, or what have you. What we're doing now is we're taking a data set where each individual respondent, each individual point, has an X value and a Y value, has an entry in multiple variables. So the example we're going to be talking about is comparing shoe sizes to heights. So these are results from the survey that we took. And what we're doing is for each person that responded, we are marking their location with, in this case, a circle, but some sort of point, where the X value corresponds to what their shoe size is in inches, and their Y value corresponds to their height. And when we make this graph, when we make this picture, we can see some sort of trend occurring. So today is talking about how do we identify these types of trends? How do we talk about what's going on here? Before we jump into what exactly these different shapes or different patterns can tell us, we want to talk a little bit about which variable we put on which axis. So we typically decide to put what we call the explanatory variable along the x-axis and the response variable along the y-axis. And what matters here is much more how we're thinking about the variables than any hard and fast rule. Switching them up certainly is usually an entirely valid thing to do, but if we are trying to ask some sort of question, if we're looking for some sort of relationship, then typically we want the x-axis to be the variable that we think is, well, explaining what's going on with the y-axis. So shoe size versus height can really go either way. You might be saying that, oh, people who have large shoes are taller, which is a reasonable thing to make some statement about. You might also make a statement like, people who are taller have larger shoes. So the narrative can really go in either direction, and it really just depends on what exactly you're trying to get out of the graph. As we'll discuss later on, we have to be really careful about any sort of cause and effect statements, but when we are choosing which variable to go on which axis, we might be imagining some sort of causality. Let's look at another example. So let's take sodium intake versus blood pressure. So regardless of the truth to a statement like this, it makes more sense to say somebody has higher blood pressure because they have a higher salt intake than it does to say somebody eats more salt because they have high blood pressure. And while it certainly is valid to make a graph, make a scatter plot with either sodium or blood pressure on the x-axis, the general convention is that we want our sodium to be the explanatory variable, and for blood pressure to be the response variable. And again, this is much more about how we intend to use these variables than it is some hard and fast rule. Now that we have that language established, we want to talk about what words we can use to describe the relationship between two quantitative variables. When we were talking about a single variable, we wanted to talk about aspects of it, like aspects of the distribution, like the shape, the center, and the spread. Similarly, when we're working with these scatter plots, we want to talk about the form, the direction, and the strength of the association. Okay, so first off, the form typically falls into the category of, is the distribution linear or not? So this particular association, if I were to draw a line down the middle of it, and we'll be doing this more rigorously in a little bit, but you could imagine a line describing what's going on. In that case, the form is something that's linear. So linear versus not linear. And we're going to have a bunch of different types of nonlinear functions or linear associations. But the main distinction we want to make is it linear or not? Right. So an example of an association that might not be linear is something that looks along the lines of, let's say, an upside down parabola. So if we have something like this, it doesn't make any sense for there to be a line to describe what's going on because we really feel like the shape deserves something curved. So if you look at the scatterplot and the shape that comes to mind is anything other than a straight line, then chances are the association isn't really linear. Like a lot of the terminology we've been talking about, linear versus not is not a hard and fast rule. It's a somewhat arbitrary choice of looking at a certain distribution and saying, yeah, I think that looks relatively linear. And there are certainly going to be times when somebody looks at a graph and says that it's linear, and someone else looks at it and says that it's not, and it's somewhat of a judgment call. Like describing symmetry, something that looks mostly symmetric, we're just going to call symmetric. Something that looks mostly linear, we're going to call linear. You certainly could look at this graph and say, oh, well, I think it actually should curve more like that. And that certainly may be the case, or it might be some other shape. But if it looks relatively like a straight line, which this one I would say definitely looks like a linear relationship, then we're just going to call it linear. The next property of an association that we want to talk about is the direction of the relationship. So possibilities here are positive, negative, and, well, no direction. A positive association is going to happen when, as we move from the left to the right, the y values are increasing. So this would be a positive association in contrast to a negative association, which happens when things are sloping downward. Right? As we move from left to right, the y values are decreasing. The way that I remember which is that if we had some line that has positive slope, it's going upward. If it has negative slope, it's going downward. It's also worth pointing out that it doesn't necessarily have to be a linear relationship in order to be able to talk about whether or not the association is positive or negative. For example, if we have a curved association like this, this would be a nonlinear negative relationship. Cool. If you can't really tell if it's going up or going down, or maybe if it's doing both, then we're just going to say that there's no real direction to the association. So our example here is going to be a linear positive association. Right. And then the last term that we want to discuss is the strength of the association. So strength talks about how close it is to actually following whatever model it is that we're talking about. And this doesn't necessarily even have to be about some linear relationship. So the contrast that I want to make is comparing this left data set to this right data set. Right. On the left, I would say that this is a relatively strong relationship. Whereas on the right, I would say that it's definitely a weaker relationship. Maybe it's, medium weak. And we can use terms like this is a somewhat strong or somewhat weak association. Like a lot of these things, this is all a relative statement, but the strength of an association is talking about how closely the data points follow whatever imagined rule there is. So if we think that our association is lending ourselves to some sort of curved line rule, then the strength is talking about how closely the data points get to that line. If they are much more spread out, like they are on the right, then it is a weaker relationship. So back to our first example, I would say that this is actually a reasonably strong, so I'm going to call it a relatively strong association. Cool. As we did with center and spread, we want some sort of concrete numerical way of quantifying these ideas of strength and direction. So the way that we're going to do that is by this measurement called correlation. Now, correlation is a term that's used slightly differently in, everyday land than it is in statistics. In statistics, it means a very specific number that is calculated that only applies to linear associations of quantitative variables. So we've been talking about how a data set might have some sort of bend in it. This correlation number only applies if the association is linear. Right at the end of this video, we'll talk a little bit about what we can do if it's not linear, but before you do any correlation calculation, you have to make sure that your association is at least relatively linear. We also want to generally avoid outliers. Outliers can really throw a wrench in these correlation calculations. They can make the number be drastically different than sort of what it should be or what it would be without that outlier point. So as we're going to keep doing, we just have to be careful when some sort of outlier is present. Okay. And then the last thing to check is to make sure that we're talking about quantitative variables. It only ever makes sense to use this if both variables in question are quantitative. All right. So how are we going to work with this number? Well, first off, we're going to call it r, so we're going to use a lowercase r. And this is not to be confused with the programming language r, but this is sort of similar to how when you're talking about the equation of a line, and we say that the line is y equals mx plus b, and the m is the numerical representation of the slope. Same sort of idea. R is going to be the is the letter that we're going to use to typically represent this correlation number. All right, so we're going to find this by calculating all of these z-scores. So we talked a couple classes ago about how the z-score is the number of standard deviations away from the mean a certain point is. So we're going to find the z-score of the x values and the z-score of the y values. We're going to multiply those together and divide by n minus 1. All right, so this is the formula. Before we jump into an example using it, because when given a formula, it doesn't really make sense, or at least to me, it doesn't usually make sense until I actually sort of get in and start using it. Before we do that, I want to point out that r is always going to be some number between 1 and negative 1. Right? So as we'll see, an r value of 1 or negative 1 are sort of the extreme options, and typically it's going to be somewhere in between there. The other thing that I want to point out is that this is unitless. And what I mean by that is r is just going to be some number by itself. And regardless of if we're talking about shoe sizes or heights that, whatever units are floating around, because we've converted to the z-scores, because we've converted to the standardized measurements, we lose all the information about units, which is actually a good thing here, because we want the correlation number, or the correlation coefficient is what this is called, to be this value that just by itself represents what the association looks like. All right, let's go through an example. So here we have a small subset of the 50-person survey dataset. And what we have are 4 people who each responded with what their height is in inches and what their shoe size is in inches. And what we want to do is we want to take this relatively small data set, and in reality we would almost never use such a small data set, but for the purposes of keeping the calculation simple, we're just doing it with n equals 4. So we've got this small data set, and our goal is to find the correlation coefficient. So we want to find the correlation coefficient. In other words, we're trying to find R. Right? And we're going to do this using this formula. So for every entry, we want to calculate the z-score of the x value and the z-score of the y value. That's what we mean by zx and zy. In other words, we want to know, for example, this 72. This 72 is certainly above average. We want to know how much above average. We want to know how many standard deviations above the mean is 72 inches. Okay, in order to answer that, we need to know what the mean is and what the standard deviation is. So we're going to take this data set, we're going to take these 4 numbers, and we're going to calculate its mean. So for the height distribution, which has n equals 4, the mean, I believe, is 67 inches, whereas the standard deviation is 3.55 inches. All right, this is certainly something that you could do on your own. We could ask R to find these things for us, but we're just going through what the building blocks are for calculating this correlation coefficient. So we can do the same thing for the shoe size distribution, where we might find that the mean, the average shoe size or shoe length is 9.9, whereas the standard deviation is 0.45. Great. So now that we have this information, we can ask, all right, how many standard deviations above or below the mean are each of these points? In other words, we can take this data set and convert it into z-scores. Okay, so just as a reminder, the z-score is going to be whatever the value is minus the mean over the standard deviation. So if we want to know what this z-score is for 64, what we want to do is subtract 64 minus 67 divided by 3.55. And remember, this being positive or negative is relevant. If we have a negative number, that means that our value is less than the mean. And if it's a positive value, then the number in question is more than the mean. So make sure that you keep that z-score number positive or negative. So for our first value, 64 minus 67 divided by 3.55, I believe comes out to negative 0.843. And we could do this for the rest of the values. Let's take 9.6. So 9.6 minus 9.9 over 0.45 should be negative 0.666. Okay, so then to finish finding R, the correlation coefficient, we want to add up the product of all of the z-scores. So in other words, we want to take this z-score and multiply it by that one. And then we want to add that to the product of these 2 z-scores, of these 2 z-scores, of these 2 z-scores, etc. We're going to add up all of those things, and divide by n minus 1. So really quickly, I'm not going to write all of this out, but negative 0.43 times negative 0.66 plus negative 0.562. Or maybe I will write it all the way out. So here we have the full equation for this correlation coefficient. So R is equal to this, which if we punch this in a calculator, I believe that we get 0.968, which is actually very high. This is saying there's a very high correlation between these two particular values. Lastly here, I want to talk a little bit about why this formula sort of behaves the way it does. Why we're even bothering multiplying z-score by z-score. So if we looked at a plot of this data, so again, we only have 4 points, but we have our high end point here, we have another point here, another point here, and another point here. Right. So here are our 4 data points plotted where we've got our x-axis and our y-axis. And the reason that we have a high value here is because the numbers that we get when we're multiplying are sort of doing as good of a job as possible of staying big and staying positive. If a particular point is above the mean in the x sense and above the mean in the y sense, so above the mean for the explanatory variable and for the response variable, we're going to get a big positive number times a big positive number. If instead we have a point down here, which is below the mean for both of the variables, well, we're going to have a fairly substantial negative number times another fairly substantial negative number. That's going to end up being a fairly substantial positive number. So actually sort of each of these ends up contributing positively to our total sum, which is then going to in turn make our end R value big. So in other words, if your data is clustered around this region, then we're sort of doing as well as possible to make a large positive R value. If instead we had a point, let's say we had a point over here or a point down here, well, this is going to have a large negative x value, but a large positive y value. Positive number times a negative number is a negative number, so this is going to contribute negatively to our total sum, our total R value. Going back to our first example, which was comparing shoe sizes to height, we can also find the R, or the correlation coefficient, for this particular example. So while we could do this by hand and go through this whole process of finding the mean and the standard deviation, transforming things into z-scores, and then adding up the products of the z-scores for each of the 50 values, dividing by 50 minus 1, which is 49. So we could do all of that, but the point of going through the process of doing this by hand is far less about learning the skill of being able to do it by hand and more just to gain an understanding of what goes into the R value. So the takeaway from this video should be much less about what the steps are to find it, and much more about the idea that we are multiplying pairs of z-scores, and that's going to encapsulate how close to a strong linear association we actually have. We can ask R to do this for us using the correlation command. So this is what I typed into R, and apparently the R value, the correlation coefficient for this, is 0.856, which is actually fairly high, even though there are some points that don't necessarily follow this linear relationship, for the most part, we can certainly see a trend. So an R value of 0.8 is pretty strong. And again, a lot of this is fairly subjective, but that's enough to indicate that, yeah, maybe there is some sort of trend happening. I also want to mention that some people prefer to use R, the correlation coefficient, by itself. Some people prefer to use R squared, and there are reasons for doing it one way or the other. This is very similar to using standard deviation versus the square of it variance. And there will be times when we may use R squared, but for the most part, we're just going to use R to represent the correlation coefficient. So just something to be aware of. We're going to be talking more in the next few weeks about what exactly we can say given a certain result. So given maybe a certain correlation coefficient that we find, what conclusion can we possibly come to? And for now, I just want to give out a warning that I'm going to give many, many times, and that is probably the most common phrase in an introductory statistics class, which is correlation does not imply causation. And maybe you've heard this before, but what it really means is just because there is a very strong association between two variables doesn't necessarily mean that there's any kind of causality going on here. So to illustrate this, Tyler Vergen came up with this website called Spurious Correlations, which uses a computer algorithm to find totally unrelated ideas that happen to line up pretty well. So, for example, per capita cheese consumption between the years 2000 and 2009 lined up really well with the number of people who died because they became tangled in their bed sheets. Okay, so just by looking at this data, we might be tempted to say, hey, you better watch that cheese consumption because that, might lead to you getting strangled by your bed sheets. All right. Obviously, that's not true. And obviously, this is a silly example, but the point is that just because there is some sort of association, even a strong association between two variables, doesn't mean that we can actually come to any conclusion unless we've set things up properly. So in a couple of weeks, we're going to be talking a lot about experimental design and how exactly we can come by these quantitative variables so that we can come to some sort of causality conclusion. Because with a lot of statistics, that's really what we want, is to be able to say, hey, A is causing B. But just by itself, if we have an association, even if it's strong, we can't necessarily infer some sort of correlation. The phrase is, correlation doesn't necessarily imply causation.